Welcome once again to my YouTube channel, Pearson and Excel International Maths by Mr. Kamotho. And let's discuss example 14, example 9 rather, the last in chapter 5, exponentials and logarithms. And let us see what happens in the real life situation. Fine, before we can discuss this example, it is important to know that we have to understand the question critically. And before then, under 5.5 exponential modeling, I would want to say something about exponential modeling as illustrated on page 116 under 5.5. And it is said that you can use e raised to power x to model situations such as population growth, where the rate increases. This is important. Where the rate increases, where the rate increases, and where the rate of increase is proportional to the size, increases proportionally. It increases proportionally, and most of the time it is proportional to the size of the population of any given moment or at any given moment. Similarly, e raised to power minus x, this one is a decrease, again decreases proportionally. It decreases proportionally, again proportional to the number of atoms remaining. But of the most importance, I want you to look at this sign. Negative signifies decrease, positive signifies increase, growth and decay, growth and decay. And with that, let us just understand question number 9. And in question number 9, we need to understand something, that the density of a pesticide, and a pesticide is a chemical used for killing insect, in a given section of field P, milligram per meter square, can be modeled by the equation P is equals to 160 e raised to power negative 0.006 t, where t is the time in days since the pesticide was first applied. And then we have a series of questions, that is part A to E. Use this model to estimate the density of the pesticides after 15 days. B, interpret the meaning of the value 160 in this model. C, show that dp/dt, or that the differential of the population with respect to time, is equals to kp, where k is a constant and states the value of k. D, interpret the significance of the sign of your answer E to part C. And of course, E, sketch the graph of P against T. Let's start our discussion and say this, that we have a relationship between the population and the time equals to 160 e raised to power negative 0.006 t. That is the relationship. Part A of the question is asking us, use this model to estimate the density of the pesticides after 15 days. Remember, in the question, we are told where t, we are told that t is the number of days after the pesticide was first applied, where t is the time in days since the pesticide was first applied. So the question is asking us, use this model to estimate the density of pest after 15 days. So it's just a matter of substituting t with 15 here, and population is going to be 160 multiplied by e raised to power 0.00006, 15. What does this mean to you? What does this mean to you? Of course, it means that when we have e raised to power 0.006 times 15, what does this give us? That gives us that. Of course, when you multiply by the coefficient of 160, we are going to find something. Of course, it is negative. The e exponential negative 0.006, of course, times 15. You have that answer. When you multiply this one by the coefficient of 160, then you have 146.23. So this is 146.2 milligrams per meter square, and that is simply the density of the pesticides after 15 days of application. Part B of the question, interpret the meaning of the value of 160 in this model. The meaning of 160 in this model, of course, you would be able to see if we want to get the meaning of 160 and it's multiplied by e raised to power anything, for us to be left with 160, we have to ensure that the rest of the part is 1. And it can only be 1 when t itself is 0. So when t is equals to 0, the population is 160 multiplied by e raised to power 0. And this is obviously 1, which is 160. So the meaning of 160 in our model is that 160 milligrams per meter square is the initial density of the pesticide. So this is the initial density of the pest, the initial density of the pesticide. That is it. And of course, now part C, show that dp dt is kp. And of course, it goes without saying because our p is 160. It's 160 e raised to power negative 0.006 t. And this one is just in the form of y is equals to e raised to power kt, or kx for that matter. And we know, according to what we understood in the previous video, that here dy dt is k e kt, and that is what we need to remember. Well, you can substitute t with x, but it doesn't really matter. Both of them are variables and they can do the same job at some point. So therefore, dp dt is simply, this is our k multiplied by 160, negative 0.006 times 160 becomes negative 0.96, so negative 0.96, and then the same expression of e raised to power negative 0.006 t, and that is our differential of population with respect to time. Yes, you can see our k now, as illustrated, dp dt is equals to kp, so our k is clearly negative 0.96, and that is now part C. That is now part what? Part C. This was part B. This is now part C, and now we are going to explain part D. We explain part D, and part B is talking about interpret the significance of the sign of your answer to part C. Now that our K is negative, our K is negative, This means, just like we have understood in the beginning of the video, when we have a negative index of the Euler's number, then this is decrease. There's a population decrease. This explains decay. There's a proportional decrease. And now that k is negative, simply because our index was also negative, then this is to say the the density of, this is simply to say that the density of the pesticide is decreasing. There is exponential decay. This is what we can call exponential decay. There is exponential decay, and that is just like it. Part E, we are expected to sketch the graph of P against T. Sketch the graph of P against T. Of course, when T was 0, we have noted that the population was supposed to be 100, or rather the density was supposed to be 160 milligram per meter square. So if this is 160, then our graph starts there. And because we have seen there is exponential decay, the density decreases with time. The density, of course, decreases with time. And that is just like the graph we need to know, because this is now P and this is T. We are when T is going to be so big a number, then the whole of this one, e raised to power a very big negative number, is going to be 1 over a very big negative number. Let me have it here. When t is going to be so much a number, then t is going to be a very big negative number, and e will be 1 over a very big positive number, because when the index is negative, then 1 over the index changes the sign to positive. So 1 over a very big number approaches 0, and 0 times anything will be approaching 0, but it does not really get to 0, and that is why our graph should never touch the x-axis. So yes, that is the sketch of P against T. And that brings us to the end of topic 5. Please get to my YouTube channel, Pearson and Excel International Maths by Mr. Kamotho. Subscribe, share widely, and we are looking forward to going through topic 6 together. Thank you so much.